Welcome and thanks for joining us for part one of our discussion. My guests today are Dr. Ann Cox. She is Quantum Information Science Technical Lead at the Department of Homeland Security's Science and Technology Directorate. We've got Donald Coulter. He's Senior Science Advisor for Cybersecurity in the DHS S&T. And also with us is Dr. Dustin Moody. He's the lead for the Post-Quantum Cryptography Project at the National Institute of Standards and Technology. Good to have you all with us today. And
thank you.
You know, we talk about cybersecurity as an operational need and as a policy requirement and all of these things, but we sometimes forget technology moves on all fronts of IT, and so therefore security technology has to move. And so our panel discussion today is going to focus on what's next, what you all are working on. So I want to just kind of ask a scene-setting question to get started here, and we'll start with you, Donald. Just basically, what are you thinking about? What are the next frontiers in research in your domain?
Yeah, so it's interesting. So we are thinking about all of the emerging technologies that are coming along, and I'm sure we'll talk about many of those. We talk about artificial intelligence. We also talk about things in terms of like microelectronics. We talk about the proliferation of operational technologies as well. And there's so many other aspects that are growing, but at the same time, cybersecurity still remains the same field with the same objectives to kind of protect our information systems from a confidentiality, integrity, and availability perspective. So what we see on the frontier really is better science and better engineering and better ways to understand cybersecurity at scale as we continue to proliferate more and more devices that have different uses and different purposes. And you have more people using them that have kind of different needs and use cases. Figuring out how to retain and focus on resilience at scale is really where we're focused on going forward.
Yeah, there's almost a fabric, if you will, of devices, of software, of people, and of functions, and even of domains when you mix in operational with, say, information, classic technology. So that's kind of a good way to think about it, maybe?
Yep, absolutely.
Okay, and Ann, good to have you. You've been with us before. I think you've been on some of our panels, but good to have you back.
Thank you.
And tell us about your next frontiers and what you generally wake up and think about that you need to do in the next 6 months, next year, and this afternoon.
So quantum information science and technology I think of it in two ways. It's both a threat and a promise. We're just starting to see a few real applications. Quantum computers in particular, there's a great variety of opinions as to when they will really be here. Some people think we'll have something in the next 2 or 3 years. Other people think it's 50 years to never. And so I think what we will see, and we're starting to see, are some individual applications coming out for very specific use cases where they're starting to make a little bit of progress. Sometimes people are using quantum just to be familiar with the technology, even though our conventional computers really can do it just as well. And then there's also, so that's kind of the promise of quantum. And then there's also what I think of as the threat to quantum. When we get what's called a cryptographically capable quantum computer, then essentially all or nearly all of our currently used cryptography will become obsolete. And so we need to prepare now. Some of our information, depending on what information that is, it may only need to be protected 2 or 3 years. You don't have to worry about that so much. Mm-hmm. But some information needs to be protected 50, 25, 50, even 75 years, and essentially a person's lifetime. And so NIST in particular has led the effort to develop protections so that our information can be practed long-term.
Got it. And that leads to Dr. Moody. That's your area, quantum. And
yes.
Maybe what exactly is it? And it's not just a linear progression from computing as we understand it. And what's your domain that you're thinking about?
Yeah, so Ann gave a good introduction there. A quantum computer is a fundamentally different type of computer than what we're used to. It operates on principles of quantum physics, different than a lot of the physics most of us learned back in high school. And those properties have some really great potential to do some computational things that current classical computing it cannot do. So like Ann mentioned, there will be a lot of really great benefits to society, not just in cybersecurity. There will be, new drugs can be designed, new solutions to logistics problems, new forecasting for weather models, all sorts of amazing things. But for cryptography, and that's where I work at NIST, we work on cryptographic standards. Quantum computers, once they're large enough, will break a lot of the crypto systems that we use today. And so we have to be ready with new solutions to counter that threat. So that's the principal focus of kind of what I spend most of my time doing right now. But at NIST, we also keep our eyes on a lot of the current research areas in cryptography, where it's going, things like fully homomorphic encryption. That helps better protect privacy of people, other techniques using threshold cryptography, trying to make cryptography as lightweight as possible. Devices get smaller and smaller, so we need cryptography that can fit on those devices and run, even though they don't have a lot of resources. So
sure,
a lot of emerging directions.
Just a detail question. Are we at the point where data can be operated on by software in the processor while encrypted? Wasn't that one of the big challenges?
Yeah, so fully homomorphic encryption seeks to do that. It seeks to operate on encrypted data, perform computations so that nobody can read it, and then you'll be able to decrypt the answer. There are some applications that can do kind of what's called somewhat homomorphic encryption. It's not very efficient yet if they try to do what's called fully homomorphic encryption. So we're starting to see some applications where they can do some interesting things. There'll be a lot more work and research needed to kind of develop it all the way to get there.
So we're kind of at somewhat quantum at this point and somewhat homomorphic encryption. And therefore, there must be a connection between seeking that homomorphic encryption and the quantum resistant work also.
Well, they're kind of two different directions. So the homomorphic encryption uses classical techniques, and post-quantum cryptography actually uses classical techniques as well, just to protect against the potential attacks from a quantum computer. So different kind of just trends in cryptography.
Yeah.
Something that I'd like to mention is a lot of people may think, why am I worried about encryption? But what they don't realize is really encryption touches all of us every day. Certainly my government equipment is all encrypted. For just the average consumer, every time you do a banking transaction, depending on the website you go to, and pretty much all of them now use some kind of encryption to protect your transactions when you buy online. And so encryption really is all around us, and it's done well enough that it's kind of silent, like we don't know that we're using it, but everyone uses encryption pretty much every day.
Sure. And so let me ask you this. In looking at protecting encryption and looking at protecting cybersecurity in the future, there's a model that is envisioned where quantum will come along and be able to, because of its power, cut through 56-bit encryption or whatever the standard is right now, and that's the end of that. Are there things that we may not be able to predict? Is there a black swan in this, an unknown unknown or a known unknown, besides the obvious one of here comes China, they've got quantum with enough quants in it to be able to decrypt this stuff. But what could happen that we don't anticipate? I mean, is that part of your thinking?
Certainly is part of our thinking, thinking about and what we're doing to...
Qubits is the word I meant.
That's right.
Gotcha.
Yeah.
So we're certainly thinking about black swan events and how do we deal with those things that we really can't predict and prepare for directly. So even as we continue to embark on research that allows us to identify a vulnerability and mitigate it and design systems that prevent those from having disastrous effects in the first place, one of the other areas that we're searching for is how do we improve our ability to understand the state of the network and the systems and devices on it, and understand all of the potential ways of identifying anomalous and potentially adversarial behavior and effects that are happening, and respond to that faster. How do we update our systems faster? How do we increase the knowledge that we have? Because we know that we're not going to be able to predict and prevent everything from happening beforehand. So even as we try to increase the inherent security of our systems, we're also thinking through all of the aspects of making systems better able to identify odd behavior, improving cyber operators and the tools they have and the education and the knowledge that they have to be able to understand when something is going awry, and thinking through how do we design our systems in a flexible manner so that if we see something that we didn't anticipate, that users use it in a way that we didn't anticipate, or something happens to it, we can kind of flip switches, we can turn things, we can reconfigure as quickly as possible.
Yeah, because what I'm driving at is, this all presupposes a model of work and of activity that we're very used to. Yep. Basically, you are at a console, it might be a mobile device, but you're basically your terminal, and then some kind of a call is going across a network, eventually a physical network. There's a process taking place, and then something is returned. That's how computing works. Is that the architecture, and I realize I'm being very basic here, that you anticipate eternally into the future, or is there some completely different mode that you might be considering, well, if this happened, then we would have to look at this? Does that make sense?
So if we really knew, then there wouldn't be black swan events, right?
Right.
There's a lot of, I'll call it resistance to actually implementing the things that we know will help with security. Something as simple as two-factor authentication is, it's kind of a bother to do that. Even for me, like every time I log into my bank, I have to wait and get the code and put it in, but I do it anyway because I feel it's important. But a lot of people will just avoid that because it's kind of a hassle. And so a lot of the problem is not only developing the things like Donald talked about and being aware, but getting people to actually use what we know works now.
Yeah, so there's a behavioral human aspect of this that also figures into this question of resilience, correct?
Yep, absolutely. Absolutely. And that's a big area. In addition to focusing on the technology, focusing on humans and how they interact with their technology is a key aspect of and not just one human to their system, but you think lots of humans interacting with different pieces of technologies, with different kind of use cases and incentive models. We have to think about those impacts of markets and economies and incentivization across those different areas as part of our overall cybersecurity resilience strategy.
And just building on that, I think like whenever we hear about some of these hacks that go on, it's not that they're breaking the crypto system underneath it. It's they had some human vulnerability, somebody clicked on a link or something like that. So it's very much a part of having to make sure people can understand the security and use it.
Yeah, and so take us, Dustin, into the lab that you work in for a moment. It's hard to envision, maybe people might like to understand what format the research takes. And what I mean is, suppose we're researching new tires, well, you mix up a batch of rubber and you can see, rub it on the road and put it on a spinner and throw things at it. In quantum cryptography, what form does the work you do day to day take? It sounds like it's pure math.
There's an awful lot of mathematics involved in it. So what we're trying to do is trying to find new crypto systems which will resist these attacks from quantum computers. These crypto systems will still run on our current classical computers because that's what everyone's going to still have for the foreseeable future. And it does take a lot of math. Mathematicians, computer scientists, computer engineers have been kind of researching this, trying to figure out what are some hard mathematical problems that even if we throw a quantum computer in the mix, they still can't break these hard problems. And over the past few decades, researchers have come up with a few different ideas, some based on what are called lattices, some are based on error-correcting codes, and then they've designed crypto systems whose security rests on these hard problems. So yeah, I'm a mathematician, and these crypto systems that we study very much involve just different areas of math.
And how does math output get converted to code at some point?
Well, it takes a whole team, and that's why it can't just be a mathematician. There has to be code for the algorithm, so computer scientists and engineers are involved. And so when we have a team design one of these algorithms, it really is a team of experts from a variety of fields who are looking at it. How am I going to implement this in hardware? How am I going to implement this in software? And so they'll optimize it even in the design so it will run really well on, on certain hardware platforms and so on. So it's a very multidisciplinary effort.
Wow, and what about at Science and Technology Directorate? How does it take us inside your labs, so to speak? And lab means bubbling flasks with flames under them, but probably not in your case.
So at this point in time, we're just kind of, I'll say, dipping our toe in the water a little bit. So because quantum information science is such a nascent field and really just developing, and our budgets are low, we don't have the money that Department of Energy or National Science Foundation has, where our budgets are pretty low. We're very focused on what our various components need. And so we're looking at the potential benefits of quantum information science, which Dustin actually mentioned one earlier. There's what's called the traveling salesman problem. That's a fairly famous problem, where you have a salesman that has to go to all the state capitals within the contiguous United States, the 48 states. And he may have various things he has to do at different places. Maybe he has to pick up things one place and drop things off another, or maybe there's time constraints or whatever. So I think of this as a multi-dimensional scaling problem, optimization problem. There's a certain type of quantum computer called a quantum annealer that looks like it's very suitable for giving us good answers to this. It's not completely clear at this point whether there's actually a quantum advantage, but we're looking at that with a problem for the Coast Guard. They have to go and service all the buoys in the U.S. waterways, both East Coast, West Coast, up the rivers, the Great Lakes, and so on. And so that kind of a scheduling problem, it can make a lot of difference how much fuel you burn or how your people are spread out and so on. And optimizing that kind of a problem may be suitable for quantum annealers. It's not clear yet. We're experimenting with that. So that's the kind of experiment that we do at S&T.
Yeah, so that takes you into logistics and operational technology
Right.
pretty deeply.
Yeah.
And you mentioned too that, and this is something we know about the Science and Technology Directorate, is that you're not necessarily at the basic research level. You're not exactly deploying technology. You're somewhere in that middle range of technology where you're looking for applications that are demanded by the various Homeland Security components. So it's kind of an applied zone of research, fair to say?
It's applied research, and it's not only things that the DHS components need, but we try to focus our dollars on things that are really unique to DHS. So we're considering some things for airport screening, for example, because kind of nobody else in the U.S. does that, right? That's a unique area for DHS. And we're just starting with some very basic research with that. We certainly don't have any results yet, and probably won't for a few years. But as I said, we're just starting to just investigate these things a little bit.
Anything to add, Donald?
I think the interesting part about some of our cybersecurity research is that with our limited dollars, we do have to focus in on unique problems or situations that larger partners may not solve inherently, but at the same time, our mission is working with our components, and especially with the Cybersecurity Infrastructure Security Agency, who does have a mission to help us protect the federal .gov network. We are focused on things that can be broadly applicable to a large set of networks, whether they're public sector, private sector, or for personal use. So a lot of the technologies that we develop can also be beneficial to the general public as well.
Yeah, and so in looking at that application kind of way of technology, the applied technology approach, you must also be looking at the threat landscape that probably informs a lot of what the solutions are sought by the components.
Absolutely. And that's more Donald's area. And threat, as far as quantum information science, is more of what Dustin is addressing there at NIST.
So let's talk, well, we'll get to that before we break.
Sounds
but I
good.
want to just understand, we heard about Coast Guard buoy servicing, which is really a big deal. It's not something the average person thinks about, but we know what's going on in the ocean waters. It's partly because of those buoys. And so to service them, the Coast Guard has to do that. What are some of the other, give us some examples of other types of projects in demand, like in the screening, for example?
Well, certainly in general screening, right, we have concern about I'll kind of mix what we're talking about, right? So in general, we want our screening capabilities, our operators and our systems that are detecting things, we want them to be accurate. They're built a lot of times as we continue to explore using artificial intelligence to help train these systems and to help us identify things. We have to make sure that those models are accurate. We have to make sure that they're retain their accuracy and ability, their predictive ability over time. And we have to be able to identify what are those risks to perturbations and adversarial inputs that may affect those models. And that brings in a slightly different perspective of thinking of how to analyze the integrity of these systems. It also makes us look at how do we protect the data that was used to train those systems, and how do we retain ownership of that and provenance of the data that's going into these systems, even as we use them, and how do we update them and keep them running with integrity over time.
Yeah, and Dustin, let me ask you the same sort of question. What do you look at in the environment? I mean, you've mentioned the model of quantum computers being able to break conventional cryptography, but there must be other threats, other environmental issues that you kind of keep in mind.
Yeah, so there's a variety of known attacks using just our current classical computers, as well as these quantum computers that are being worked on and developed. For example, there's things known as side channel attacks, and that's where your adversary is able to get access and perhaps measure the power or the time that it's taking your system to run. Even sometimes they can do things like just listen in on you using the acoustics, and they're able to do some calculations and come up with some of your secret information. There's some fascinating research where adversaries can do some pretty innovative and interesting things and leak part of your secret key, and that might make it just easy enough that they can then get into your system somehow. There's a variety of attacks that we have to protect against in cryptography.
Yeah, I understand they can even recognize keystroke patterns and pressures and so forth.
Yeah, so we have to try and design crypto systems so they'll resist all of these things. Yes.
They can tell if you're left or right-handed, probably.
Yeah.
Make sure, if I could, I'm sure they could. Yeah. Which way is that mouse pointing? Well, that's a good note to take a short break on, and we're going to return shortly. We're going to take a pause on part one of our discussion with Dr. Ann Cox, the Quantum Information Science Technical Lead at the Department of Homeland Security's Science and Technology Directorate. Donald Coulter is Senior Science Advisor for Cybersecurity at DHS S&T, and Dr. Dustin Moody, lead for the Post-Quantum Cryptography Project at NIST. We'll be back for part two of our discussion after this industry perspective. Let's now go back to the studio for more on the Cyber Leaders Exchange.